So you've got your data and you'd like to do a regression, and you find that your dependent variable is on the ordinal scale. So you read around on the internet and you find in some papers they treat it as if it were continuous and run a normal regression. So you wonder to yourself, okay, is that the thing to do? Well, there is a type of regression that takes into account that your dependent variable is ordinal, and so doing such a regression is probably better, unless there's some reason why you can treat those ordinal variables as if they were continuous. So I'm going to give you one example today. I'm going to go through it first, very basic detail, and then we'll go through it again and talk about all these kinds of issues, because you know when you're doing some analysis you've got loads of issues. Okay, so it's important to go through those issues, otherwise it's kind of just leading you into false hope that it's easy to run. So let's say I've done an experiment on a sample of 208 people. I've divided them into 4 groups, each of 52, and I let them taste the cheese. So there's 4 cheeses labeled A to D, and then I ask them to rate it on a scale of 1 to 9, where 1 means it's really, really poor, and up to 9 where they think it's brilliant. So if we look at like cheese A, 7 people rated it as a 4, 19 rated it as 7. We see there are some ratings which have zeros in them, so no participant actually registered that. 1, 2, 3, for example, on cheese D. That's to bear in mind later when we're looking at the output. Now, a question for our regression might be, okay, I want to see whether there's a difference in the liking of the ratings of the cheeses, and can we say something about how much someone prefers a cheese A to a cheese C, say? So we can answer such a question with a regression, and we note that the rating scale here is ordinal. So we're going to treat it as ordinal, not continuous. Okay, this is what my data set looks like. So I've got 3 columns, one for cheese, and you see I've got 9 entries there because I've got 9 ratings, you see. So ratings 1 to 9, and then the third one is the counts. To run the regression, I first have to weight it by count, so I go to data, weight cases, and then move the count into the frequency variable, which I've done already. Okay, now I run the regression, and you do it as follows: analyze, regression, ordinal, and then you move the dependent variable, here being rating, to dependent. I have cheese. Now there's 4 types of cheese. It's a categorical variable, so I move it into factors rather than into the covariates. If I had a variable that were continuous, I would move that into the covariates box rather than to the factor box. Okay, next I go to options. I'm just going to tell you this. By default, SPSS sets the link function to a logit, but if we click under there, there's lots. We'll talk about this on the second pass, right? For everything we're doing, we are doing a logit link. The choice of link affects the interpretation of the parameter, so bear in mind that this is for a logit link. And for a model with the logit link, this is called the proportional odds model, or otherwise known as the ordered logit model. Next we click on the output, and we just go down to the bottom and just tick here, test of parallel lines, and continue. And then we click OK. Okay, so we get a load of output. As you know, SPSS spews out a load of output. We go to the table, it's the second one, called model fitting information. The output here tells us how our model compares to the model with no factors or covariates, in other words, just an intercept. This is otherwise known as the null model. What we're interested in looking is here, final, and looking at this chi-square value here, which is 148. We're interested in the p-value for that, which is basically it's tiny. The null hypothesis is that our model doesn't do any better than the null model. Another way of saying it is that none of our factors help to predict the ratings. Here it's clearly rejected because of the small p-value, so we reject the null. So our model is better than the null. Now this is not such a great test statistic because, you know, anything is better than doing nothing, so you know that doesn't really tell us anything. More importantly is how much better does this model, our model is better than the null model. Okay, now then we go to the box underneath, which gives us a goodness of fit test. The null model null hypothesis here is that our model is like adequate relative to the perfect model which perfectly predicts all the cell counts. We report either the Pearson or the deviance. I think it's popular to do the deviance. So it's about 20. They're very similar anyway. 20 and significance it's 0.5, so it's bigger than 0.1 or bigger than 0.05, so no evidence to reject the null. That the null being that our model is adequate. So that's a good sign. Okay, the pseudo R, we don't I don't think it's common to report this, so we'll just ignore it. Pseudo means it's pretend anyway. Okay. Next is the parameter estimates. This is the whole point of running this regression in our case, because we'll try to address our questions. But before we do that, let's look underneath here. I don't know why they put this right at the end. I prefer to put it early in the front because it's a test. Test of parallel lines. Okay, that sounds a bit abstract. The null hypothesis is that this parallel line assumption holds. Okay, it's even written down here where it is. So basically, to go further, we would like this assumption to hold. So do we reject it? Look at this general chi-square about 20.3, p-value 0.5, so bigger than 0.05, so we no evidence to reject it. Okay, indeed it's bigger than 0.1, so there's no evidence to reject the null. So that's good. So for our model, it is satisfied. Okay, now this is where you have to roll up your sleeves and really focus. Parameter estimates. Alright, there's a load of stuff dumped over here. Okay, we have 4 cheeses, and being categorical, it means we set up dummy variables. There are 4 cheeses. SPSS by default sets the one coded the highest as the reference group. So we've got 4 cheeses, so this cheese 4, which I believe is cheese A, is the reference. These, the threshold, are basically my intercepts for each of the cheeses. For interpretation, we ignore that. Okay, it's more important these are like my slope parameters. This is what I'm interested in interpreting. In normal regression, these are like my intercepts. Regression intercepts. We don't place much interpretation on those. Okay, now here's the thing. We're interested in interpreting then the slope parameters. The slope parameters tell us something about preference, so about the ratings of these cheeses compared to cheese 4. Now, just a warning right away is that if you read around, the package SAS deals with the setup of the model slightly different to SPSS, Stata, and R. So if you're going to be reading around and you're going to see in a SAS application, by default, SAS does it slightly differently. So then the interpretation is not exactly the same as ours. It will be only if you do a minus times a minus by the coefficient on the SAS, or if you reorder it. Okay, so just bear in mind if you're going to read around, don't want to get confused. We're dealing with SPSS here. Okay, the way SPSS sets it up is these are our betas, right? We've got one for each of the cheeses. If the beta is bigger than 0, that implies that since we have got categorical variables, these being types of cheeses, that you are more likely to get a higher response for that cheese compared to the reference category here being cheese A. So basically, like a positive beta is like a positive effect. It's more likely you're going to rate the thing on a higher, because remember, rating, low numbers for low rating, high numbers for high rating, and a positive beta means like a more positive rating. Likewise, a negative beta means like you're more likely to rate it lower compared to the reference category, here being the cheese 4, cheese A. So we'll do it in 2 steps. Just first of all, forget about the significance, they're all significant anyway. Look at the cheese 1, it's positive. What does that mean? It means that a person is likely to rate cheese 1 more highly than cheese 4. Cheese 2, that's a negative, so that means the person is likely to rate it lower than cheese 4, and cheese 3 is also a negative, so same thing. So in that respect, it's very similar to the normal regression. A positive beta means like a positive correlation between X and Y, but that's only because of the way the model was set up. I'm not writing any equations here, so I'm just telling you. Okay, but we can do better than that because that's just a sign, but how about the magnitude? 1.613, how can we interpret that? Well, for the logit link, if you take the exponential of the number, that will give us the cumulative odds ratio for a 1 unit increase in that x. So let me give you an example and that'll make more sense. So let's take exponential of this thing here. Okay, the odds ratio is about 5. This tells us for cheese 1, I think it's cheese D, the odds of rating, given a rating, bigger than or equal to any number you like from 1 to 9, 0 to 9, sorry, is 5 times higher than the odds for that for cheese 4, which is cheese A. In other words, that magnitude that's at 5 gives you like an idea how much more highly that some regards the was rating this cheese 1 compared to cheese 4. Okay, let's do cheese 2 as well. Okay, that's got a minus 1.71, so take the exponential of that, it's 0.1. So literally this says for cheese 2 the odds of someone rating it bigger than or equal to some value on the rating scale is 0.18 times the odds of cheese 4. Since this number is less than 1, that's equivalent of saying that the odds of a high rating for cheese 2 is 0.82 times lower than for cheese 4, by doing 1 minus that number there. And we can do the same for cheese 3. Now another thing we can see is the comparative signs, because everything's at the moment compared to cheese 4. But if we look at the order, we can see then that cheese 1 is the best because it's bigger than the number is bigger than all of them. Followed by cheese A. When I say best, that means preferred. Followed by cheese 2, and the last is cheese 3 because it's got the most negative sign. Okay, so that's the first pass. So I'm going to go through it again. Let's talk a bit more in detail about, or just not in detail, just give you a bit more information about some of these things. First, we'll go back to the choice of the link function. So we chose the logit link, and now I can tell you the logit link is like one of the more popular ones, and it's convenient in terms of interpretation point of view because if we take the exponential of the slope parameter, it gives us some kind of odds ratio, here being in the cumulative odds ratio. If you use any of these other links, then the interpretation of the beta will not be odds or odds ratio. Those of you actually learning about ordinal regression might encounter the adjacent category logit, ADL, which the parameters may be interpreted in terms of log odds. So if we take the exponential, it is an odds. So does it matter which of these guys you use? Well, for a point of interpretation, I've just explained why the logit is important. Sometimes the model doesn't fit so well, and so you try these other ones. It's like a trial and error, and to find out whether it works, or makes your model fit better. And SPSS has a guide on which one to use, saying that it depends on the like the distribution of the choice of in our case, the ratings. Is it skewed to the left, skewed to the right? But okay, so we can forget that bit anyway. So just know that we've got all these other kinds. Right, another thing, this example has been very limited because my independent variable has just been a factor. Okay, so I haven't introduced any covariates, so it could be some other things that impact your rating. So this example has been very limited, but you can think of like if you've got other covariates, could be like age in there, factors, could be other things like ethnicity. Also, we can introduce like interaction terms as well. So for all these things, that the interpretation, I'm going to have to go into that, but it's too much for like one video. Next, I want to go into this goodness of fit test. The goodness of fit test, as with all your other goodness of fit tests, relies on the expected cell counts, most of them being bigger than 5. Rule of thumb is like more than 20% of your cells should have expected cell counts bigger than 5. So here we've got 22.2%, so I should kind of just be a bit cautious about the result I've got. How can we deal with something like that? Well, just like with crosstabs, we can kind of combine some of our categories, like rating 8 or 9. I could compare those, but since I had a problem with lower ratings, I could combine the first two ratings, rating 0 or 1 or something like that, or 1 and 2, 3 or something like this. The other thing is it's a large sample test, so we know that as n increases, then both these Pearson and deviance will be basically approximately the same. So that's why you can see the numbers are so similar. That's why it's like we don't really care which one we're using. Alright, so for our test, it passed. How about if it doesn't pass? If we fail, if we fail here, being to reject the null, what would we do then? Well, one reason it could fail is because of our independent variables. So we might have to. It might be because we haven't introduced like some important factors or covariates in there. So we could try that. Another thing we could try is to change the link function, or do both. And if I could just rewind a bit. If we got expected cell counts, a lot of high proportion of expected cell counts, I said we could combine groups, but we could also then use compare nested models. So a smaller to a slightly bigger model using the difference of deviances, because then that's kind of a bit robust to low cell counts. Okay, this parallel lines assumption, let's look at it because it's a bit weird. What does this mean? Okay, so parallel lines makes you think of like a graph, doesn't it, with lines? And yeah, it's a graphical way to kind of think about what's going on here. And what the proportional odds assumption or parallel lines assumption says is, what it says is that the odds ratio is the same no matter how you split the ratings here. So let's say we're looking at the odds ratio between cheese D and cheese C. I get an odds ratio for like 1 to 3 compared to 4 to 9. Then whatever that number is, it'll be the same between, so long as I've got these two cheeses the same as between 1 to 5 compared to a rating higher, 5 to 9. So however you split the rating into two parts, comparing one to the other part, the odds ratio will be the same so long as it's the same cheese. I guess like in layman's terms, it might be like saying it doesn't matter like what value you choose to be like the threshold of saying like and dislike. You know, you might say like 4 downwards is like my dislike, and higher is like. It doesn't matter how you choose that value, that's not going to affect the value of the odds ratio. Can I say also then the parallel lines assumption, it needs to be tested irrespective of the link function you choose. So it's not just for the logit link. Now how about if this assumption doesn't hold? Don't panic. Right, what do we do? Well, one thing to do is to relax the assumption of parallel lines, believe it or not. So in other words, it allows the odds ratio to change if I just kind of split these into two, like 1 to 3 to 4 to 9. Now might be different, the odds ratio, if I did 1 to 5 compared to 6 to 9. SPSS doesn't allow you to do that, but if you use a package like R, that has something, so where you can kind of run the this ordinal regression without the parallel lines assumption. What you can do with R is instead you can kind of then forget that it's ordinal and revert back to a multinomial model, or you could run like pairwise binary logistic, so compare, like in our case, run it as a regression, run it as a binary regression comparing like these cheeses one to the other, like D to C, D to B, D to A, and like that. Or then you could even revert back to thinking, okay, let's pretend our ordinal variable is actually continuous and see where we go. One thing though, that if you instead you run like a binary logistic and compare the odds, and you see the odds are similar to the ones you get from here, even if the parallel lines assumption doesn't hold, means like, okay, it was broken, violated, but it didn't affect the results too much. Okay, so I hope I've given you a flavor of ordinal regression, and if you want to find out more, that's when you need to find out about interpreting the where you got the covariates, like continuous x's, independent variables, and interactions in your model. But if your application has everything that's categorical, then you're in a good position.